So our next speaker will be Bob Krueger, and he's going to be talking about disjointness amnesia, random Erdo s-Ko-Rado, and its joint work with Joseph Balag and Howran Luo.
All right, thanks for the introduction. Thanks for organizing everything here. So yeah, today I'm going to take maybe a different approach than most other people I've seen at this conference. Stylistically, at least, I'm going to write things instead of having slides. So it's going to be a little bit slower, but hopefully give you a little bit more time to think about things. So yeah, the title of the talk is Disjointness Amnesia, which is a little cheeky, but I'll explain it later. First, let's start out with a definition that I've already written down. We're going to be considering families of sets. A family is nothing special, really, it's just a set of sets, but saying set of sets all the time is a little confusing. So whenever we've got a collection of sets, I'm going to call it a family. So a family of sets is intersecting if any two elements of the set have a non-empty intersection. Okay, so the most basic question you can ask here is, what's the largest intersecting family of all the subsets of 1 up to n? So this bracket n right here is the numbers 1 up to n, and 2 to that is just the power set of this set. Okay, so unfortunately I have to spoil the answer for you, but there's 2 parts to this, right? A lower bound and an upper bound. So for a lower bound, let's try to think of a construction, and a natural construction is what I'm going to call a star. So these are all sets containing some fixed element. So some fixed I from 1 up to n, just pick 1, say, for concreteness, and this has size exactly 2 to the n minus 1. Okay, so half of this power set. And now, why is this tight? Why is that the best you can do? Well, for the lower bound, I'm going to divide all the subsets of 1 up to n into complementary pairs. So every subset of 1 up to n is disjoint from its complement in 1 up to n. And so you can have at most one of those 2 sets in your family. And so there you go. You can have at most half of the sets, subsets of 1 up to n. And so the star is tight. Okay, so we've got this nice warm-up problem under our belt. Now let's go on to the star of the show. Our question is, what's the largest intersecting, here I should really have said subfamily, intersecting subfamily of, now not all subsets, but all subsets of 1 up to n of size k. Okay, so by this I mean all subsets of size k. Okay, now the answer to this question depends slightly on the values of n and k, how they compare to each other. So let's think for a moment. If n is less than 2k, then if you take any 2 sets of size k that belong in the integers 1 up to n, they will intersect, right? So the answer is just n choose k, right? You can take every single subset and it's a intersecting family. If n exactly equals 2k, we can think if I have a subset of size k, the only k set that it's disjoint from is its complement. And so that's why you can get half of the sets. It's pretty much the same argument that we had in the warm-up question. Okay, now things get a bit harder when n is bigger than 2k. And here we'll just come up with an upper bound first. So stars actually give a good, oh, sorry, lower bound. Yeah, I messed that up. This should be an upper bound, right? We have an upper bound on the maximum size. Stars our construction will give some lower bound on the largest subfamily. So if I'm looking at all the K sets that contain the element 1, then I need to choose the K minus 1 other elements of the K set from the N minus 1 other elements from the ground set, 2 up to N. And so this is the conjecture, right? Is this the maximum size of the largest intersecting subfamily? And this is what the Erdo-Krueger theorem says. So if you've never heard of Erdo-Krueger, now you know what it is. So Erdo-Krueger says these are the largest. Okay, great. And there's several different proofs of the Erdo-Krueger theorem throughout the years. I think this, I forget when the theorem was originally written, but probably back in like the 40s or something. And so since it's so old, there have been many extensions to it. And that's what we're going to talk about today. So some basic extensions to get familiar with it is that stars not only are the largest intersecting subfamily, but they are unique. Stars are unique. So there's no other intersecting subfamily of all the K sets of this size. They all have to be stars. Another question you could ask as an extension of Erdo-Krueger is, what's the maximum size not contained in a star? So we know what the largest subfamilies are, largest intersecting subfamilies are. What if you ask them to be what's called non-trivial, so they don't all just contain the same fixed I like a star does? And so this is known as the Hilton-Milner theorem, if you want to look that up. Another interesting extension, more modern, is that, say if I know that my set is almost intersecting, meaning that there's few pairs of sets in my family that are disjoint from each other, then that implies that my family is close to a star, in the sense that the symmetric difference between my family and some star is small. And so this is a theorem from the past, I don't know, 7 years from Dawson Tron. Okay, so this last one I think is particularly interesting because it's sort of commenting on the robustness of Erdo-Krueger. So that's going to be our next leading question: is how robust is Erdo-Krueger, which I'll abbreviate EKR. In particular, we're going to take this lens. Is it still true, it being Erdo-Krueger, if I forget that some disjoint pairs are really disjoint? So this might sound a little funny, but I'll introduce another way of looking at things that will make this formal. Okay, so this is our lead. We're wondering how robust is EKR. So let's reformulate it. We're going to define the Kinesio graph K and K to be the graph on all the K sets of 1 up to N with the disjointness relation. With the disjointness relation. So two K sets are adjacent in this graph if and only if they are disjoint. Okay, and so just to understand this definition, what does an intersecting family look like? Well, an intersecting family, every pair of sets is, they have a non-empty intersection, so they're not disjoint. And so that means that that is an independent set in the Kinesio graph. And so already immediately, what does the Erdo-Ko-Rado theorem say? It says that the independence number, so alpha is the symbol for that, the independence number, the maximum independent set of the Kinesio graph has size n-1, choose k-1, which, and it's achieved by stars, the same construction. Okay, so now we can get to the forgetfulness part, right, which is consider a random version of Erdo-Ko-Rado. And there's a couple different ways you might consider a random version of Erdo-Ko-Rado, but we're going to consider this one, and it's also a measure of how robust Erdo-Ko-Rado might be. So consider including the edges of the Kinesio graph one by one in a random way. So the Kinesio graph has a lot of edges. We just start with no edges, and we just throw in edges one by one. Our question is, when do we expect the Erdo-Ko-Rado theorem to hold? And by this, I mean that the largest independent set has size given by the Erdo-Ko-Rado theorem, n-1, choose k-1. Right, because if we start with no edges, well, the whole graph is an independent set, so the independence number is n choose k. But as we throw in edges, we reduce the independence number until finally we get to the independence number of the whole Kinesio graph. Okay, so this is the question, and conveniently, our theorem answers this. And so there's a few different ways you can answer it. One way is you can say, we can tell you just about when you would expect this theorem to hold. So I can say that after, let's say, take epsilon to be a small constant, after this many, I'm just going to write some complicated expression, but don't mind it. So after you reveal this proportion of the edges, after this many edges are revealed, the Erdo-Ko-Rado theorem, or your largest independence number, largest independent set, this holds. So I can give you some sort of precise, like, oh, if you reveal this many edges, this is what you would expect. Of course, I can't expect this to always hold, right? Maybe I was given edges in a bad order, or luck was against me. So I can say it holds with high probability. So probability tending to 1 as n tends to infinity. But I can actually say something a lot more precise, which is a lot more illuminating. Which is that the first time, as you're introducing these edges, the first time the stars are maximal independent sets, meaning that you can't add another vertex of the Kinesio graph or another K set to a star to get an intersecting family. first time the stars are maximal is the first time the max size independent set is what you want it to be. Right, and this first condition is clearly a necessary thing for the second one, because if your stars aren't maximal, right, that means I can add something to the stars, so I can get and get an independent set, so I can have an independent set of n-1 choose k-1 plus 1. And in some sense, what this hitting time statement is what this sort of thing is called. What this hitting time statement says is that the hardest thing to achieving this independence number is making your stars maximal. Now, unfortunately, we don't prove this for all n and k. We spotted an error in our proof a little while ago, but hopefully we can fix this soon. Anyway, I think I'm out of time, so I'll open it to questions now.
So let's first thank our speaker. Now, does anyone have any questions?
I've got a question. So do you have to wait for all the edges to be revealed to get EKR holding with probability 1 always?
Yeah, so if you want it to, well, actually, no. So if you can still leave away few deliberately chosen edges and still have the maximum independent set, have this size. One easy way to see that is that, so one question to ask is how many edges, what's the minimum number of edges in a set of size n-1 choose k-1 plus 1. All right, because basically for EKR not to hold, you need a set of that size to be independent. And so you need to get rid of all the edges that are in a setup for that size. And so you can ask what's the smallest number of edges in a set of that size, and that's how many you would deliberately have to forget for EKR not to hold with probability 1. So yeah, you can still forget some. And that is another interesting question, which I don't think is fully resolved, but is certainly easier than the probabilistic version.
Thank you.
Sorry, you might have mentioned this earlier, but in this theorem, what should be my intuition for like the size of this constant that we're multiplying by the number of edges in the graph? Like,
oh, this thing?
Yeah, like that that left hand side. I haven't done the asymptotics. Like what's roughly what kind of thing is it?
The intuition is precisely this hitting time statement, actually. So this is the first thing that we came up with, but really the second part is what's driving it. So this calculation right here is just, this is after this many edges, you expect your stars to be maximal.
Okay.
And so it's really the hitting time statement that is giving you a much more precise bound. Yeah. That's the intent.
Any other questions? If not, let's thank our speaker again.